Hello and welcome to Phased Array Tutorials. This is tutorial 2 on using Ansys HFSS, CST MW Studio and Keysight EMPro antenna pattern files in SystemVue phased array environment. What you will learn in next few minutes is how to deal with array antenna and select your own custom element pattern options and bring over the file formats from these three popular electromagnetic tools. And we will look at what kind of file formats are supported inside SystemVue. After understanding a bit of basics, I will show you with one of each of these pattern files a phased array simulation inside SystemVue environment. And also at the end, we will do comparison of 4x4 array pattern data generated from ADS using RF Pro, and then using the same data inside SystemVue for our phased array system design. So you will get all the required confidence and information of being very comfortable bringing over these kind of antenna pattern files and use it for your own phased array system design. Before we start, subscribe to my channel. Once you subscribe, don't forget to click on the bell icon to enable all the notifications. And after you watch the video, give it a thumbs up and share it with your friends and colleagues who may be interested in watching similar tutorial. All right, let's get started and understand each of these points here. So let's quickly review what we did during the last tutorial in our phased array playlist. So in the last tutorial, I went over basics of each of these blocks. So we assembled a typical phased array system. We defined certain variables and we looked at the ways to plot the 3D far field as well as plot the 2D far field cuts in our phased array analysis. Now I have modified the last settings which we used during the last tutorial a little bit to suit my antenna design. So here I changed the frequency to 2.4 gigahertz and number of X and Y elements to be 4. Now I'm all set to start using those pattern files inside SystemVue. Now to do that, we can go to this array antenna component where we define the array configuration. Under element pattern tab, remember we use isotropic pattern for every radiator during our last experiment. Now under this option, we also have pattern file option. Once we pick that, you could choose the file type. And currently in SystemVue, you can bring over the files from these three popular 3D electromagnetic simulation tools. Now for EMPro, HFSS or CST, for each of those file options, you get different mapping options. That means you may have one radiation pattern file which you want to apply for all the elements. If so, you can select the option of same for all elements. But if you have individual, far field radiation pattern file for every component, then you can use individually and then you can have a list of far field pattern files which you could use inside SystemVue. Or you could do some custom mapping. That means, for example, let's say you are building 8x8 antenna array, but you only have 8 pattern files. Then you can define your own custom file mapping to use those 8 radiation pattern files for all 64 elements in the manner you want. And finally, you can browse to the file name where your far field data is stored. Now, before we jump in and start using some of this data, it's always a good practice to refer to SystemVue documentation about beam pattern. In this beam pattern documentation page, you can see all the details mentioned about the traditional antenna radiation pattern file. Also, specifically on the pattern file, where we discuss about EMPro, HFSS, and CST. And there are a list of options available here, and this documentation is provided in great detail. So feel free to go through it carefully before you start, doing this kind of simulations. All right, so let's go back and let's go down a little bit and understand. For HFSS, SystemVue will support these 5 format of files because user can export data in variety of formats. So all these 5 formats are supported. However, depending upon which format of data you have, it may contain all the information necessary for your phased array system design directly, or sometimes SystemVue may need to calculate that based on the data. And those details are mentioned right below this table, and feel free to read that carefully so that you can have the right kind of data so that you can minimize as much mathematics as possible and rather use directly the information coming out of your 3D tool. Similarly, for CST, here is the file format details located. All right, so with this detail, let's go back to our system view environment. And here, what you're seeing is 4x4 array simulation with an isotropic radiator, and that's the 2D cut. So before we start experimenting anything, let's mark that trace. Let's freeze that trace using this checkpoint so that this trace gets freezed for easy comparison. Now in the array element, let's go back and change it to pattern file. Let's bring over EMPro data first. And here I will use same for all elements option. In terms of file name, I will go ahead and pick a file with the extension .uan. This is the extension which EMPro uses while generating the far field pattern file. And here at the bottom, you can also see the preview of the file regarding the information contained in that particular file. We click OK. Now, when we are using one pattern only and then applying for all the elements, one thing which you need to be careful to get the right far field pattern. Under array configuration, you should define the right distance between the elements, and that can be done using wavelength option, or you could go and enter the absolute dimension as per your array lattice design. So if this is not correct, then you will not get the right far field pattern when you use those options. So be mindful of this fact here. All right, so in my case, I'm selecting half wavelength because I know my antenna array design has elements a spacing of half wavelength. Now, once we are done, very simple, I browse to this file, we click OK. And now once we run simulation, we can see how this 4x4 array behaves with EMPro data. And you can see it's largely the same, just a side lobe is slightly different, and there is a slight variance in the main lobe, but overall it's quite fine. Now at the same location, we can go to element pattern again, and instead of EMPro, let's bring in HFSS data. And again, I will use the same option, same for all elements, but now I need a new file because this is an EMPro file. So let's go back to the same location, and HFSS usually will export the data in .csv file, and you can see the file format. And this is one of the 5 formats which are supported, as I just showed you in the documentation, and you can refer to the data here. All right, so once you have this data, nothing else to be done here. We already take care of half wavelength spacing, or you can set it depending on your array antenna design. We go ahead and simulate, and now we can notice how the radiation pattern changes with a non-ideal resonator or non-ideal patch element which we designed inside HFSS. Now, while importing this pattern, if you really want to see how an individual radiator element pattern was before you start using it, you can always click on display pattern, and it will show you the far field of the element which you just brought in. And here you can see the radiator's far field performance, which we just used for all our 16 elements here. All right, now let's go to CST and again use the same method. And in CST file, the usual extension is .ffs. And once you browse to that file, again, you can see it's a CST far field source file. And then you can look at the format, and it is exactly the same format as recommended in the documentation. All right, so once we use that, file format, we just go ahead and run simulation. Now you can see the antenna radiation pattern is kind of completely different, and also the far field pattern looks quite different compared to HFSS and EMPro, because obviously all these 3 antennas are different, they are not same. So their characteristics is different. Hence, the resulting far field pattern is also different. So this is one of the condition when I only have one radiation pattern file and I'm trying to apply the same file for all the radiators. But as I showed you during the RF Pro phased array video, if you have seen my antenna array simulation video, each element, depending on its location, may have slightly different far field pattern. And overall, those patterns will have some implication on the overall phased array beam pattern data. So in reality, for more realistic simulation to reduce again the mathematics, I should be using an option not same for all elements. However, you can always use this. It's not that bad. You can ideally use individual for all, or each element. So that means in my present case, when I have 4x4 array antenna, I need to have 16 radiation patterns files. And I have generated those 16 radiation pattern files from EMPro. And you can see under this directory, I do have 16 UAN files. Now, another question which might be coming to your mind, well, I have 16 radiation pattern files, but if you look at the field here, it can only support one file name. How I am going to type in, 16 file names here, or in your case, it could be 64, 128, or whatever number of files. So how I am going to do that? Well, SystemVue uses a very simple logic or a naming convention and an assignment convention when you are in this situation. So let me explain what. So recommendation number one or rule number one, when you have this situation, all your file names should be same. And you can see here the string of each file name is called pattern in this case. Then depending upon the order of your radiator, you just simply increment it by 1, 2, 3, 4, 5, 6. So this is how SystemVue will know where to start and where to stop, and it will automatically pick those files for you. You don't need to specify 16 or 64 file names here manually. Just use this simple, naming convention in your far field files and everything will be taken care by SystemVue. So here basically you just pick the first pattern file, click open, and in this list you will only refer to the first file. Rest everything will be handled by SystemVue automatically. Also, depending upon how you have extracted that radiation pattern, you may or may not have array factor included. So in my case, I know when I extracted these 16 radiation pattern files, I only excited one element at a time and all other elements were silent or not excited. So that means my array factor is already included in the radiation pattern which got generated. And if so, I need to select this option so that SystemVue does not apply any additional array factor. So once you select this option, you don't need to worry about this distance unit anymore because all the data is now self-including here, and it avoids double compensation for the array factor or double calculation of array factor. So this is rule number one. The rule number two is which pattern file gets assigned to which radiator, right? Now, again, SystemVue recommends a simple methodology. So if I go to antenna configuration and just to show you array lattice configuration, and let's look at the top view. Now in SystemVue, the lower left element is always element number one. So your pattern 0, 1 data as per my list will get applied to this element here. And the increment happens column wise. So this is second element, third element, fourth element, and if you had more, then your fifth, sixth, and seventh. So the first column will be covered first. Then it will come back here. So in this case, this will be element number 5, 6, 7, 8, then 9, 10, 11, 12, 13, 14, 15, and 16. So using the index in your file name, it will get applied to the right radiators. So when you are extracting this data from your 3D tool, make sure you extract it with this naming convention or this location convention. Very, very simple, nothing complicated to understand. All right, so now once I have data, I applied individual files for individual elements. I accounted for element array factor. Now, before I go and simulate it, let's say if I want to see radiation pattern for each of those radiators before I use it, how can I do that? Well, remember we talked about display pattern earlier. Now you have 16 files, so you need to enter the index. So let's say I want to see element number 1 index, which is currently corresponding to pattern 01. If I enter this index 1 and click on display pattern, now you can see the pattern data of the first element, and notice here the gain is around 6.34 dBi, and you have this kind of radiation pattern for the first element. Now for second element, if I enter the index 2, click on display pattern, now you can notice the gain is around 6 dBi as opposed to 6.3 dBi, and this pattern is slightly different. So this way you can keep typing and keep clicking on display pattern and scroll through all of those pattern files which you have to make sure right pattern file is getting read for the right index. All right, cool enough. All right, so now once we are done, we are all set to perform our simulation. Now go ahead and perform simulation, and now let me clear the checkpoint. So I click on the graph and say clear checkpoint. Now this is my beam pattern data for 4x4 array antenna, and you can see gain of this far field of this antenna is around 18.6 dBi. So that's my overall gain from this array. But now how do I know how good or how bad is this data, whether SystemVue did an accurate enough job? And remember, it can never be 1:1 data most of the time, but the main lobe has to be absolutely correct. And inside lobe, if I have 1 to 3 dB difference, I'm still kind of okay. I can manage that. But largely, the pattern data should behave very close to how my full 3D electromagnetic tool has behaved. Now, in order to do that, I can export this data into an external text file, and then I will export the data from my ADS RF Pro or EMPro or HFSS, whatever tool you might be using for your array antenna design, and then we will just simply compare it. So let's see how we can do that very easily. Now remember in the last tutorial we talked about data set. So after I perform simulation, I have this data set. Now if I open this data set here under beam measurements, I do have a phi cut directivity information. So if I click on this measurement, you can see the phi cut for theta minus 90 right up to plus 90, and this is my far field data. Now I can export this data into an external CSV or a MAT file. To do that, I simply click on this icon here called export, and now I can choose the format which I need to use. So in my case, I will use CSV, and then I don't need a header information or an independent variable. But let's pick independent variable, which is basically your phi axis. But I don't need any header information. That means where this data is coming from, what's the matrix type, and so on. So I'll remove the header, export, and now this data has been exported to a folder where I have this workspace. So that's done. A CSV file is generated. Now I go back to my RF Pro, and this is the demo I showed you in one of the earlier tutorial videos of RF Pro. I have this 4x4 patch array antenna which I simulated, and currently what I am looking at is a directivity plot of that antenna. And also I talked about how can we create a 2D line graph in that tutorial. So I already have that graph here. And you can notice I have placed a marker which is showing gain of around 18.6 dBi, which is very close to what SystemVue was showing. So prima facie, they look pretty good. But I still need to compare the complete pattern with each other. So from this graph here, I can go to File, Export Data, and now I can export this data into an external text file. Click Export, select the location where you want to export the data, and here let's call it rfpro underscore data.txt. Now once we have this data exported into a file, I can go to that folder. And now here you can see I have RFPro data, and also I have the beam measurement phi cut directivity from SystemVue. So let's open that in Excel first. So that's my SystemVue data of phi cut. Now I can open the data generated by RFPro and simply use a notepad editor. And here you can see RFPro by default is exporting data for theta minus 180 to plus 180. And I have data from SystemVue from minus 90 to plus 90. So we'll go ahead and select a block of data from here from minus 90 to plus 90. Now, if I want, I could have wrote a very simple script inside SystemVue because we do have MATLAB. We could have called both of these files, did all the curve plotting and so on and so forth. But I just wanted to keep it very, very simple using layman method. Once I select this data, just right click, copy, and let's go back to our Excel and paste this data back in Excel here. Now I can select these two columns and this third column because I already have the x-axis. I don't need it. Once I have the data, let's go to insert, go to chart and insert an XY chart here. And now if I make this bigger, you can notice the comparison. The blue trace is from SystemVue here because that's the series 1, and series 1 is your first column or the second column here. And the orange trace here coming out of your RFPro. And you can see the main lobe is exactly 100% matched between those two tools. Even the null locations, the first null location is absolutely bang on, except the levels are different. The side lobe is slightly different. But again, you expect that from a full 3D electromagnetic tool to a system engineering tool. But largely it has an excellent match, and I have confidence that all the data which I have brought into SystemVue for doing my system phased array analysis, I can totally rely on it, and I can go ahead and do the further operations as needed for my phased array system design. So let's go back to our agenda. I just showed you all the key points here so that you can feel fully comfortable bringing over your antenna pattern data from your favorite electromagnetic tool inside SystemVue in variety of formats. You can either use the one radiation pattern file for all the elements, or if you have different files for different elements, feel free to use that. That will give you a little more realistic information in your phased array system design. So that's all for this video. Hope you like the content presented and it will be very useful for your system design job. Don't forget to hit the like button of this video and subscribe to my channel for more such interesting tutorials. Have a great time designing your systems, my dear friend, and have a great day ahead.